Does anybody have something hanging from their rearview mirror right now in their car? A little chain with something on it. Is there anybody in the room who does have one of those? Okay. So you understand that when you're driving your car, it swings around? So when you accelerate, it comes backwards towards you, right? When you hit the brakes, it goes forwards towards the windshield. That's because whatever it is has inertia. It doesn't want to move and won't begin to accelerate until there's an unbalanced force acting on it. And when there's an unbalanced force, then it will accelerate. So if your car is accelerating, for a moment, it won't want to because it has inertia. So until there's a force in the direction of motion, the thing that's hanging from your mirror won't accelerate. So if we read this, it says a small mass is connected to a thin cord that hangs from the rear view mirror of your car. When you accelerate forward, the cord swings backwards to an angle of theta. What is the acceleration of your car? And what will be the angle that mass makes when the car travels at constant velocity? So two different questions there. It says, when you accelerate forward, the cord swings backwards to an angle of theta. What is the acceleration of your car? Well, question number 2 is super simple. So I could do a harder one, or I can do question number 2. What do you guys want to do? A harder one? I think it's probably better if you see a more challenging one. So let's do, we haven't talked about springs yet, so we'll wait on the spring question. I like question number 4. Let's do question number 4. It's got a lot of stuff in it. I think it's a good one to use. It says a 2 kilogram box is attached to a string that is also attached to the end of the ramp. The ramp is able to be lifted to make an angle theta while the box is on the ramp. If the ramp is frictionless, what max angle can be attained before the tension in the string makes it to 10 newtons? Everybody follow along so far? So I think the question wants theta. What angle can we make it to until the string's tension is 10 newtons? You guys read that same way I do? We're going to do a force concept problem here because it seems like it's about forces. Can you see why I think it's about forces? They mentioned the tension in the string is 10 newtons. That sounds like a force. That's how I'm kind of seeing that this is a force question. So let's take a look at this problem. A 2 kilogram box is attached to a string that is also attached to the end of the ramp. The ramp is able to be lifted to make an angle of theta while the box is on the ramp. If the ramp is frictionless, what max angle can be attained before the tension in the string makes it to 10 newtons? All right, so we're going to do part of the elevator question. And so I'm going to do, say, the first part of the elevator question, okay? Which is talking about the force on the elevator for each stage of the elevator's motion. Is that good for you guys? Now, the person's in the elevator, so I'd say they have a combined mass of 325. All right. So, acceleration. It says the elevator accelerated upwards at 2 meters per second squared for 2 seconds, then traveled at a constant velocity, and then slowed to a stop in 1 second. Now, I know that what this is telling me is that the elevator made it to 4 meters per second, right? It accelerated at 2 meters per second for 2 seconds. So if I use a motion equation real quickly, I can, in my head, state that, well, V equals AT plus V naught. The elevator started from rest, accelerating at 2 meters per second squared for 2 seconds from rest. Means the elevator is now going 4 meters per second. But then it says that the elevator slows to a stop in 1 second. Well, if it slows to a stop in 1 second and it's traveling 4 meters per second, V final will be 0 equals A times 1 plus 4. Right? Same relationship, V equals AT plus V naught. I'm just solving for the acceleration. And it looks like the acceleration is negative 4 meters per second squared. I'm just doing the kinematics on it. That's why we learned kinematics, right? Velocities are easier to detect than accelerations. But this tells me that the acceleration is downwards. That's good to know. Kind of knew that, but now I know it for sure. So, again, we want to see as many of these as possible. We're going to do number 11. I like number 11 because we already did half of it. We're just going to do it again. And I think 11 is complicated enough to have good stuff in it for you guys to need to see the practice. It's a tough one, though. So for you guys who are doing this for the first time, I'd really pay attention to this one. It says you push down on the handle of a 20-kilogram lawnmower. The handle makes an angle of 40 degrees with the horizontal. The grass is tall enough that a resistive force that's proportional to 50% of the normal force acts on the mower. That's probably a good piece of information to file into the back of your head, that there's a resistive force. Doesn't say it's friction, but they're giving us some assigned force, something that sounds like it opposes the direction of motion of the lawnmower. Would you guys agree with that statement? Okay, so I'm going to tuck that away, that there's some resistive force acting on the lawnmower. How hard, that's not good. That's not good. How hard do you have? That probably should be how hard do you have to push down the handle of the lawnmower to move at a constant speed? All right, I'm going to do just that one. And you guys can do the one that has the acceleration in it for homework. Sound good? How hard do you have to push down the handle for the lawnmower to move at a constant speed? Sounds like a briefly draw a quick problem here. All right, so lawnmower, wheels, wheel, and handle. There, lawnmower. Okay for you guys? Good enough? You making fun of my lawnmower over there? Yes. My word. Is this a first law problem or a second law problem? So I think we can all probably, I don't know if we can all agree on this. The Snickers in the room are giving me pause, but I think we can all agree the idea is the lawnmower is going to go this way. So, but it's traveling at a constant speed, so we're making this a first law problem. All right, I'm going to start identifying forces that are acting on the lawnmower. Can you name one? Gravity, that's a good one. What else we got? We have a resistive force from the grass. I don't really know how big to make this because it says it's 50% of the normal force, but I'm going to put F with an R here for resistive force from the grass. Is there anything else? There's a force of me pushing down. It says that the handle makes an angle of 40 degrees with the horizontal. So eventually I'll have to deal with that 40 degrees, but I'm going to draw this as my pushing force. Anything else? Go ahead.
The contact force from the ground pushing up.
Yeah, I think we have a normal force here from the ground pushing up, and that should be straight upwards. Normal force. We know from the problem that the resistive force is 50% of the normal force. Right, that was given to us in the problem. So that means the resistive force is 0.5 times the normal force. Okay? Just writing something down that they gave us in the problem. Eventually, this resistive force is going to be given a name, and this percentage is going to be given a name. You guys who had AP1 know it's called the coefficient of friction, but we'll be coming back to that. So I don't want to use the big term for it yet, but it is in the other problems. You'll see the word coefficient of friction. It is always a percentage of the normal force, just like this. But let's keep going. I have drawn all the forces acting on the object. This is our free body diagram. We need to make a coordinate system that could be used to solve this problem. So I think an appropriate coordinate system would be one that's aligned with the most number of forces possible because the system's not accelerating. So just like before, I'm trying to utilize my procedure, but also we were given priorities. And the priorities for the coordinate system are ones that align with the most number of forces if the system's not accelerating. So I can align this with 3 of the forces, right? It makes no sense to say, turn it to be aligned with the pushing force, because now I'd have to break up 3 other forces into their components. So we will line it up this way. I'm going to choose this way to be the positive x direction and this way to be the positive y direction. All good for you guys? All right. Where does the 40 go? Does 40 go here or here? Hold up fingers. I can't trust you guys. It's either 1 or 2. Don't scratch your nose because you're concerned that people will know. We're about evenly split. And then we have about 6 people who haven't voted. In first period, I had to give a geometry lesson. Looks like I have to do that here too. I'm sorry. That's the horizontal. It was 40 degrees with the horizontal, right? So if I take this and push it through, this is 40 degrees. So vertical angles are congruent. So this must be 40 degrees, right? That means it's 2, not 1. And trust me, last class period, I had to use the alternate interior angles are congruent. So you guys need to remember your geometry. All right, I have to break up any off-axis forces. I have 1 off-axis force. So I'm going to break it up. So I've drawn a triangle. I've wrapped it around my angle. My right angle has to be here by definition. And I think this one's pretty straightforward in that the adjacent side is going to get the cosine. And the opposite side is going to get the sine. Any questions about those choices? When you do that, you are effectively taking away the original force that was there and replacing it with 2 components. So this is really what I have left now. All forces that act in either x or either y. So now, net force in the x direction has to equal 0. Net force in the y direction has to equal 0. So we need to figure out how to apply Newton's first law in this arrangement. Looks like I just had to read my set of instructions, which say add up all the forces in the x direction, taking into account their direction, and set that equal to 0. I see only 2 forces acting in the x direction. I have the part of the pushing force and the resistive force, and they are now set equal to 0. Any question about that? All right. I now need to do the same thing in the y direction, and I have, it looks like 3 forces that act in the y direction. I have normal force minus the weight minus a portion of the pushing force. And that has to equal 0. Any questions there? Okay, we're all good? All right. That's what the force concept model does. It creates relationships. So I have created a couple relationships. I also have this. So what did the problem want us to solve for? Do you remember? How hard do I have to push? It wants the pushing force. Now, I will point out you have 3 relationships and 3 unknowns, right? The resistive force is an unknown, the normal force is an unknown, and the pushing force is an unknown. You have 3 relationships and 3 unknowns. You will have to put them together to figure out the size of the pushing force. That's algebra. All right, so I'm just going to go through this and solve this for the pushing force. So there's a couple things I think I need to do, but one of them is probably substitution. And the first substitution I see is this one. And then I'm going to be able to substitute n in there too. let's have an elevator. I gotta draw something here. How about, here's our elevator, and then there's a person inside the elevator. Whee! And the elevator is attached by way of a cable. And there's three different things. There's it accelerating upwards, it traveling at a constant velocity, and it accelerating downwards. All right, those are three things you heard. Those are three things I heard. All right, let's do this. It's a force concept model problem because they're asking me for a specific force. They want the force of tension in the cable. So I'm going to start by recognizing whether this is a first law problem or a second law problem. And I don't know that it's the same for each part. I think for the first part, where we're talking about the elevator accelerating upwards, it's a second law problem. It says it in the problem, it's accelerating. So I think this one is going to be a net force equals ma. Then it says that the elevator travels at a constant velocity. That sounds like a first law problem. And then the third part says that the elevator comes to rest. That sounds like an acceleration. So I think that's going to be a second law problem. So I think we're doing a problem 3 times. One for each section. I'll do, I don't know, first section. Let's start with a free body diagram. What forces are acting on the elevator? Gravity's acting on the elevator. That's an arrow that I will draw straight downwards and label mg. Or weight. It doesn't matter how I label it, but this is an acceptable label for weight. Is there anything else in contact with the elevator? Yeah? The rope, the string. So what kind of force would that be? Tension. The elevator is accelerating upwards, so my thoughts are the tension must be greater than the weight, so I'm going to draw it so. Now, if I'm going to just do this portion of the problem, then I have to see if there's any other forces acting in the system, and I think the answer is probably no. There's no surface in contact with the elevator, and there's no resistive forces to speak of in this problem. So I think we have exhausted our list of forces. We have a free body diagram. The next part of our free body diagram is to draw a coordinate system that could be used to solve for our answer. So I'm going to choose a coordinate system, and I'm not going to sweat this one very much because it's a one-dimensional problem. So although I'm making a coordinate system, it's a one-dimensional problem. So I don't really have to worry too much about this. There's my coordinate system. And I'll make this the positive x direction, and I'll make this the positive y direction. All right, going on to my next part, I am supposed to apply Newton's laws to this problem. Well, net force in the y direction equals ma. I've aligned the y direction with the direction of the acceleration. And net force in the x direction, although this is redundant, equals 0. Remember, you're supposed to, as a priority, line up your coordinate system with the direction of the acceleration. The reason you do that is so that one of these gets ma and the other one doesn't. So that's on purpose. We're doing this purposefully. All right. When I look at this problem now, I've written down which of my Newton's laws I'm going to use. Now I have to follow the instructions set out by Newton's laws, which says to add up all the forces in the y direction, taking into account their direction, and set it equal to 0. That's what this statement says. Add up forces, which are vectors, in the y direction, and set them equal to, I said 0, I'm sorry, set them equal to ma. So I think there are 2 forces acting in the system. There's tension, and then there's weight. But weight's acting downwards, so I'm making it negative. And I have to set this equal to ma. I followed the instructions. Now, when you're done with the force concept model, this is what you're left with. So of the procedure I gave you, the procedure ends here. Now, you want to find out if you can use whatever this procedure is to answer the question that was asked in the problem. And the question that was asked in the problem was to solve for the tension. So can I solve for the tension with the information that was provided? I think so, yeah. It looks like to do so, I will get tension by itself, like so. And then I know what all of these things are. So the mass is 325. G is 10 and A is 2. I just pulled the M out front so I can just add those two numbers together. All good to you guys? Any questions about this? Pretty straightforward, isn't it? I kind of feel like I don't have to do too much work for the next one, because the next one just wants us to figure out what the tension is when it's traveling at a constant speed. What changes when I apply that parameter to the problem? Is there a change in the weight of the car? Is there still tension acting in the cable? Yeah. But now the net force isn't equal to MA. What's the net force equal to? 0. So for part 2 of the problem, the only real change here is that this is 0. Which, if that's 0, looks like that's how the problem changes. All good? The third part, though, that might throw you, because they don't give the acceleration, do they? Did you guys notice that? That's the issue for. Looks like this will be an acceleration of 4 meters per second squared downwards. So when we do the last portion of the problem, the part where we're trying to figure out what the tension is in the cable when the elevator is slowing down, I'm still going to have net force in the y direction equals MA. I'm still going to have tension minus weight equals MA. But now this is tension equals MG plus M times A. I put a negative 4 in there because my acceleration was negative. Yep.
Is it possible to just rewrite it as 325 times the parentheses 10 minus 4?
Yeah. But that confused somebody a minute ago, so I didn't do it that way. Now this tension, I want to point out, is less than the weight of the car. This sometimes is confusing for folks. But just because the elevator is slowing down doesn't mean there's not tension in the cable. It just means the tension is less than the weight. It is the weight that is slowing the elevator down. We've just reduced the tension so that the weight can take over and change the velocity of the cars. That makes sense? There's nothing new pushing down on the elevator. We're just using the elevator's own weight to do the work. All right. Relatively simple example. You guys can redo the problem now with just the person. But let's, like I have a ramp. And the ramp has got a box on it. So there's my ramp. There's a box on the ramp. And it's connected by a string to the end of the ramp. Now let's make it a ramp. All right. Does this sound like the parameters of the problem? And I can increase this angle, and we're trying to increase the angle until the tension equals 10 newtons. All right. Is this a first law problem or a second law problem? Is it going to accelerate? No, we want it to stay on the ramp, so I think it's a first law problem. Let's draw a free body diagram. that tells us what's happening to the box. All right, step 2, make a free body diagram. Can anybody name a force acting on the box? Gravity, that's right. Always be the first one to say gravity. Makes it sound smart. Makes it sound like you know what you're doing. So I'm just going to put mg here. I will probably change what I put on these from time to time just to keep you on your toes. Is there anything in contact with the box? Name one thing in contact with the box that's applying a force. The string is definitely attached to the box and is applying a tension. Tension has to be in the direction of the string, so anything else in contact with the box? The ramp. The ramp provides what kind of force? A normal force. It has to be perpendicular to the ramp. So anything else acting on the box? Is friction acting on the box? No, they say it's a frictionless ramp, so I don't think so. I think this is it. Now let's apply a coordinate system. That will be the next step. So I'm going to come up with the coordinate system. There is no acceleration, so I don't have to worry about lining this up with the acceleration. I do have to worry about the second priority to try and make my problem easier, and that would be to try and line it up with as many forces as I possibly can. So as I make my coordinate system here, I think if I was to choose how to line it up, this is the way it comes, naturally, but I think it'd be best to line it up like that. That way it's lined up with 2 of the forces, not 1. I don't have to. I could line it up with the weight, but it seems like this way I have 2 forces that are lined up already. Does that make sense? All right, so I'm going to do that. I'm going to go ahead and make this the positive x direction, and this one the positive y direction. I have to put theta someplace, so do I put theta at 1 or I put theta at 2? I mean, you have to know. And I'm not trying to confuse you. I will give you a way to do it if you can't figure it out if I'm looking. So here's the way to do it. This angle that we want to mark here is always the one that's aligned with the weight and a line drawn through the normal force. Okay? So the one that is a line drawn through the normal force is that one, and this is the weight, so it's going to be 2. That's where theta goes. It's all these little things that add up. All right, I'm going to break the weight up into components. I will wrap a triangle around the weight, like so. This is the right portion of the triangle. Make sure you get that part right. And opposite gets sine, adjacent gets cosine. So mg sine theta here, and mg cosine theta there. All right, I've made a coordinate system. I've broken up my forces into their component vectors. I now have to apply Newton's law. So I will have net force in the x direction and net force in the y direction, and they both equal 0. Add up all the forces, taking account direction, and set it equal to 0. So let's start with the x direction. I see 2 forces in the x direction. I see tension and a part of the weight. Do you guys see that? So I will have tension minus mg sine theta. I'll set that equal to 0. In the y direction, I have 2 forces as well. I have the normal force, and I have mg cosine theta. I set them equal to 0. All right, I have exhausted everything Newton's laws can do. The force concept model gives me a relationship. I have 2 relationships. Let's go back to the question. Sounds like one of these relationships will help me more than the other. They tell me that the mass is 2 and the tension is going to be 10. So it says in the problem. I want to know what angle brings the tension up to 10. If you look closely at this, it's T equals mg sine theta. So clearly, as theta gets bigger, tension gets bigger, right? Because sine increases as theta increases. So I know that as the angle gets bigger, the tension is going to get bigger. If theta were 0, there'd be no tension. It would just be flat. There'd be no reason for the string to hold the block at all. So we start getting tension the moment we start lifting the ramp upwards. So I'll put in my 10 for t. M is 2, G is 10, sine theta. I think this relationship will solve our problem. This is going to be sine theta equals 0.5. I know you're all going to your calculators, but come on, sometimes the math isn't that hard. 2 times 10 is 20, and 10 divided by 20 is a half, right? And you should know which angle gives you 0.5. Do you? Everybody who's been studying should know that sine of 30 is 0.5. If you don't know that, don't worry. In a few weeks, you're going to be doing the unit circle. And once you start doing the unit circle, you'll know all about 30, 60, 90 triangles and 45s and all those things. You'll know them in radians, you'll know them in angles. It'll be so much fun. And you'll enjoy it immensely. I can't wait for your pre-calc escapades. But if you needed your calculator, then you'll get 30 degrees. Unless, of course, you forgot to set your calculator to degrees and you have it stuck in radians, then you're going to get something else entirely. Make sure your calculator is set up correctly, please. Are you seeing these problems? The problem isn't going to be using the force concept model, probably. Force concept model generates relationships. It's what you figure out what to do with those relationships that matter. All of these homework questions are the same. All right. So let's have our small mass. We'll just say a box. And I want you to think about it. It's connected by way of a string to the rear view mirror. This is probably what it looks like when it's just hanging there before you've gone anywhere, correct? You're just sitting in the car, you're stopped, you're at the light. And then when you accelerate away from the light, it swings backwards towards you. Does that make sense? So you are here, holding on to the steering wheel. Does that look like you? A little bit? I'd say it's pretty close. One of you has kind of a beard thing and eyeballs and nose. Curly hair. Okay, I've covered a few people now. See? Looks just like you guys. But you get the idea that it swings backwards in angle theta. That okay? Are we all good? All right. So, is this a first law problem or a second law problem? Oops, I lost the thing. I'm sorry, what was that? It's a second law problem, right? We are accelerating in the car, so it is a second law problem. So that means net force equals ma. We're going to draw a free body diagram depicting what's happening here. Can you name a force acting on the mass? All right, so I'm going to draw a downwards arrow to represent gravity. And I will label it W. It is true, though, we know W equals mg. Let's keep that in mind. They gave us the mass. We can use m as part of our problem here. Is there anything in contact with the block? The string. The string is in contact with the block, so the string must be applying what kind of force? A tension force. So I will draw a force to represent, or an arrow to represent the tension acting on the object. Is there anything else in contact with the box? Nope, this is it. The two forces acting on the box. If I recall, the next step would be to apply a coordinate system that we could be used to try and figure out what's happening to the box. A coordinate system is just a x and y, so I'm going to draw an x and y. Now remember, our goal here is to align it in such a way as to make it easy for us to solve our problem. So how would you like to align it? There's two priorities. Priority number one is to align it in the direction of the acceleration, or to align it with the most number of forces possible. Is our system accelerating? What direction is the mass accelerating? Now this one often confuses you guys. because it swung backwards. Some of you think it's accelerating backwards towards you. That's not what happened. It's traveling with the car. Is the car going to the left or to the right? Car's going to the right, so the box must be accelerating to the right. That has to be the direction of the acceleration, because it's traveling with the car. And because that's the direction of the acceleration, I'm going to line up my coordinate system so that the positive x direction is in the direction of the acceleration. It said that's your first priority in deciding how to set up a coordinate system, is to make one of your x or y directions in the direction of the acceleration. All right, this will be the positive x, that'll be positive y. All right, so the next thing you have to do is take any off-axis forces and break them up into components. Are there any forces that are off-axis? Yeah, the tension is off-axis. I need to find out where that theta goes. And I have to do it relative to x and y. So do you guys know where it goes? Does it go here or here? Just hold up a number of fingers. So that way everybody has to do it. All right. You guys are students of what's that called? Geometry honors, right? You successfully passed geometry honors. You had to get it to Algebra 2 honors, and then pre-calc. So you even took an exam on geometry. Now, if you've never had geometry, you could be forgiven for not knowing that it's 1 and not 2. But let's talk about why, because for whatever reason, my mind did not forget everything from geometry like yours. If I put two parallel lines here, and I have a transverse that cuts two parallel lines, these two angles are called alternate interior angles. And if you'll recall from geometry honors, alternate interior angles are congruent. You're going to have to remember things. I know I'm asking a lot. This one wasn't too rough, though. So that means this is theta. All right, continuing my problem, I have to break this up into component vectors. So I'm going to wrap a triangle around my angle. And I struggled with a student yesterday during tutoring who still has a hard time figuring out how to deal with breaking this up into components, but the opposite side is always going to go with sine, and the adjacent side is always going to go with cosine. So this is going to be t sine theta, and that's in the x direction, and this is going to be t cosine theta, and that's in the y direction. Any questions about those choices? All right. Step 4, apply Newton's laws. We said that this is a second law problem, but we aligned our coordinate system so that the second law portion was in the x direction. This was purposeful so that we could say that in the y direction, the net force was 0. Right. By making sure the direction of one of your coordinates is in the direction of the acceleration, you are making the other one equal to 0. That's on purpose. All right, follow the set of instructions. Add up all the forces, taking into account their direction, and set them equal to ma. I see only one force in the x direction. Do you guys see that? So I will write t sine theta equals ma. All good? All right. In the y direction, I see two forces. Do you see two forces? I see t cosine theta upwards and weight downwards. So I will write t cosine theta, make it positive, minus weight equals 0. All right. Now, everything we have done from the moment we drew the free body diagram to the moment we got to now had nothing to do with what was in the problem. All we did was apply the force concept model to develop a couple of relationships. And we now have two relationships that come from the force concept model. So we just applied a set of steps. We have not answered the question. We've applied the set of Newton's laws And now we're going to see if we can answer the question with the information that was presented. But all we get from using the force concept model are two relationships. So everybody got it? That's all it can do for us. They indicate that I need to find the acceleration in terms of theta. So that's what we're going to do. I have two relationships here, and I want to find the acceleration in terms of theta. So this first one has the acceleration and theta, but it also has other things in it too, doesn't it? Tension and mass. Didn't say anything about mass or tension, so I probably want to get rid of tension if I can. They did mention that there's the mass involved, so I think I can use mass in my answer. And on your test, I will tell you what can be in your answer, but this is homework. So homework might not always be like that. Is that okay? I know that t cosine theta equals the weight, and I know weight is actually equal to mg. So if I do some substitution from things I know, I can write t cosine theta equals mg. It looks like I have a way of eliminating tension between these two equations. Do you guys see that? So I'm going to try to. Now, I think you guys would probably do substitution. I think that's your major method for doing things. Like you'd solve one of these for t and plug it into the other. Does that sound like something you would do? Okay, we're gonna learn something new today for math. Do you know that you can divide both sides of an equation by the same thing? Have you heard that before? So I'm gonna divide this side of the equation by t cosine theta, and I'm gonna divide the other side of the equation by t cosine theta, except t cosine theta equals mg. So what I'm doing is I'm dividing these two equations by the same thing, but I'm putting what they equal on each side. Has anybody ever done this before? Dividing one equation by another equation? You have now. Right? You have now. So you've seen it done. I want to do it this way because if you'll notice on the left side, the t's will cancel out. Do you see that? And on the right side, the m's are going to cancel out. This happens a lot when you have equations that have such similarities. So get used to seeing stuff like this. Dividing one equation by another equation. And yeah, t's cancel out and m's cancel out. What's sine over cosine? So I'll just multiply both sides by g. This tells me that I could make a simple accelerometer, a device that measures acceleration by just measuring an angle. A protractor and a hanging mass would do it. They'll have accelerometers on rides at the parks at Busch Gardens. This is a cheap way to make one. You don't need any fancy stuff. Your phone does it by doing something else, but you can make an accelerometer that tells you the acceleration. Now, this one's no big deal. It requires that you have gravity, but if you'll take a look, if you think just a little bit, you know that the stuff can't swing all that much, but if it swings, say, 45 degrees, that's an acceleration of 1g, right? Because tangent of 45 degrees is 1. You know, so stuff that swings in your car, I bet you can probably brake at 1g and have stuff swing about 45 degrees in that direction. I don't know if most of your cars will accelerate at 1g, but they might get close. Some of them are pretty good cars. I've been in the student parking lot. But this is an answer to the question. But also, it's an answer to the second question, which is what would the angle be if the acceleration were 0? It looks like from this equation, if I put in 0 for the acceleration, theta would also have to be 0. So at constant velocity, the thing just hangs there. That's reasonable. It's not accelerating anymore. There doesn't have to be a component of force in the direction of motion. So there, we've done question number 1. Let's try question number 2. I'm trying to show you how you apply the force concept model to your homework.